Good afternoon everyone, thank you for joining me on this video. I am Mr. Ish. Today we are talking about derivatives of integral in terms of the continuation of the fundamental theorem of calculus video I've presented previously. The fundamental theorem of calculus is not a difficult theorem to accept, but it is a difficult theorem to understand. It requires a certain amount of blind faith in that, as I've told you, if you take the derivative of an integral, you arrive at the original function. And then I've told you when you have a function, you take its integral and then you take the derivative of the antiderivative, you end up back to the original function. It's not always possible that when you've taken an integral of a function, or if you have an original function, it's not always possible that that original function can be easily integrated, because sometimes seemingly easy looking functions are very difficult to integrate. To go from the loop where you are starting with an original function and you're doing its integral and you're coming up with the antiderivative and then you're going back using the derivative to show that indeed your answer was right, you took its derivative and you should end up back at the original function. Sometimes it's not easy at all when you have an original function to even find an integral and arrive at this step, let alone take this step and work backwards by finding the derivative of your antiderivative and going back to the original function. Sometimes this right here, this part over here is difficult to even perform, because sometimes very seemingly easy looking functions are very difficult to integrate. The fundamental theorem of calculus requires a certain amount of blind faith, and I've told you that the derivative of an integral is always going to lead you to the original function. You can easily prove that when you're doing a derivative of any kind of a function. If you're doing a derivative of any kind of a function, let's just say a, b, f of t in dt, you can arrive at some value and that value will be your original function. This right here is what I want to talk about in today's video, and I can only show you this loop when it comes to easy examples, because sometimes when you complicate the examples to do the integral becomes very difficult, if not impossible. But you have to blindly accept the fact that once you've determined your original function, if you were to do the integral or the derivative, you can work backwards. You can work in this form of a loop. You can do the derivative first and take the integral back, or you can do the integral first and take the derivative back to the original function. Let's look at what I'm actually talking about with regards to this statement over here. Over a given interval, if a function is continuous over that interval, the function has a point at every point on that interval where you can determine its derivative. If you can determine the derivative of an integral, you can end up back at the original function. So let's look at this statement over here a little more thoroughly in this video. If you have an expression which is this, that you're doing the integral of some form of a function and we want to determine what the original function was. Why do we want to do it? Because it's part of understanding the fundamental theorem of calculus. If you have a definite integral from 1 up to x, x can be any variable, you know 1 is a constant of this. How can we determine what the original function was? Because the subject of this is taking a derivative of an integral. Why? Because it takes you back to what your original function was. These are like examples of very easy questions. Let me show you. I want to show you the procedure as to how I would solve these. And someone may disagree watching this video, but this is how I would do it. It's a standard procedure, and I would apply this standard procedure to all such type of questions. Start with a substitution of u is equal to x, and then we can substitute for this. Now watch what I'm doing. We're kind of using the chain rule, even though we don't have to use the chain rule. And it's not hard at all as to what you might be thinking. If u is equal to x, you have u and then 1. You have this part right over here rewritten over here, because from this we have to determine the derivative of this integral will lead to an original function, and the du or dx of this x. When you see all of this play out, you'll see what I'm exactly talking about. The derivative of x is just a 1, so that comes out at the beginning as just a 1. This u has to be substituted for right over here. You get u squared, and what do you end up putting u over here for? Was your original substitution. You get x squared. This right here represents what your original function was over this interval. What was our original function? F of x was equal to x squared. You see how something was originally f of t is equal to t squared? It has become in the standard notation of f of x is equal to x squared. And we know here we're talking about the interval 1 comma x. If supposedly you were to determine the integral of that function, this, remember, is an easy example. Why am I using this? Because I can actually do the loop that I was talking about. With easy questions, you can do the loop. Look, or if I did the integral of this function right here, x squared dx is my integral, and I'm doing it over this interval 1 and x. If I were to do the integral of this, and we have yet to learn the actual procedures for integrals, but assuming we knew them, we would get x cubed over 3, and we would still have to do the definite integral over this interval. If you were to do this, what would you end up getting? You would put x in place of x over here, you'd get x cubed over 3 minus, the difference between this is the upper limit and the lower limit of an interval when it's integrated is always deferred by means of a minus sign. You'd have a 1 cube over 3, which is a 1 over 3. This right here represents our antiderivative of all of this. Now if you were to take, and remember I'm talking about the loop, after having determined the original function, we're doing the loop where you can do the integral and then you can take the derivative and end back to the original function. Now this part right here, if we were to take the derivative of this, look right here, the derivative of this it's a constant, it'll be a 0, but let's just do the derivative of this. You'll do x cubed over 3 minus derivative, and I'm just separating them, of this constant. This constant derivative is zeroed out because derivatives of constants are just zeros. You're just left with doing the derivative of this variable aspect, the variable aspect of this antiderivative. When you do this using the procedure of the power rule, you do 3x squared over 3. This 3 comes as a coefficient, the power of 3 is reduced by 1, hence you get 2 over here. When you simplify this, you get x squared, and you end up back at the original function. So you've seen over here, using the property of, basically it's part 1 of the fundamental theorem of calculus, whereby if you take the derivative, and you could present this original question in a textbook in this format. You're doing the derivative of this integral. That's how the questions would be presented to you. The question would be in this form: what's the derivative of this integral? If you were to take the derivative of this integral by means of this chain rule, which you don't have to, but I'm just prescribing that you do, because it's a foolproof method, especially once these variables become composite, then you can actually arrive at an original function. If the original function is easy enough, you can test it out by using this loop procedure, where you do the integral of it over the interval, and then you do the derivative of that antiderivative and come back to the original function, and we have shown you that. I want to show you another question, and then we'll get things slightly more complicated. Alright, let's look at this question over here. We have to find the derivative of this integral, and in questions like this, when you see them from a textbook, they're always using here the t, dt, and then the t notation over here, and you have to find the derivative in terms of the x variable. But the question is over this, over the interval 0 and x, you have to find the derivative of this, because the derivative of an integral will lead you back to your original function. And this will be the last, in terms of easy question, I'll present to you, because with this, when we do the actual answer, we can take it through the loop and show that our answer is indeed right over this interval. Because then things get too complicated and determining the integrals becomes sometimes next to impossible. Now look over here. I'm going to use again the chain rule. You don't have to. If u is equal to x, let's look over here. Derivative with regards to u. Now all you gotta do is write what you see over here with the substitution u over here and 0 over here. You write everything else over here as you see it. 1 plus root t dt, you close this up, right? Then you write du over dx, and you just have x over here. The derivative of x is just going to be a 1. The next step, all you're going to do is substitute u into this over here. You'll get 1 plus root u, then resubstitute back 1 plus root x. So what are you essentially getting as your answer over here? 1 plus root x is your answer you're getting. That's your original function. This right here represents your original function right over here, 1 plus root x. It basically mirrors exactly this. You see 1 plus root t, you're getting 1 plus root x. F of t was 1 plus root t, f of x is 1 plus root x. Now look over here, this is just a procedure for finding out what the original function was. Now look, we have to just do the integral of this over this interval, 0x 1 plus root x. I'm just writing root x as x to the 1 over 2 dx. You can separate this out, and we'll learn all of these procedures in a very upcoming video, how you actually do the integration. You'll separate this out. dx plus, I've just separated this by means of the plus sign. You have an x0, x to the 1 over 2 dx. If you do the integration of all of this, you'll get x plus x to the 3 over 2 over 3 over 2. If you simplify all of this, remember this right here is all over the interval x and 0. If you simplify all of this, you'll end up getting x plus 2 over 3 x to the 3 over 2 over this interval x and 0. Now look over here, we still have to actually complete this part. When you do x and 0 in this place, you'll just end up getting an x. X minus 0 is just an x. You'll see all of this, what I'm talking about, when we learn the actual procedures for calculations of the integration calculations. Over here you get x to the 3 over 2 minus 0 to the 3 over 2, and you'll still end up getting 2 over 3 x to the 3 over 2. This right here represents the integration of this original function. Now all we have to do is finish the loop. We've done the integral part, we'll do the derivative part of this. The derivative part of this. When we do the derivative of that, this right here, you know you can separate these out by means of the plus sign, but I won't. X becomes what? It just becomes a 1. Remember, the power 1 comes here as a coefficient, and the power is reduced to 0. You get 1 times x to the power 0, which is just 1. Now look over here. 3 over 2 comes as a coefficient and multiplies by 2 over 3. 2 over 3 times 3 over 2, it balances out, it cancels out, you get a 1. And 3 over 2 is reduced by 1, you get x to the 1 over 2, which really is 1 plus root x. This 1 plus root x exactly mirrors your original function right here, which was right over here. This is exactly the gist of this video, is what we're talking about. Taking the derivative of an integral to yield the original function, and you can in some instances take the original function, do its integration. Remember, the fundamental theorem of calculus is not always necessarily applicable only to indefinite integrals. You can use it with definite integrals where you actually have an interval. Anyhow, once we obtained our original function, we showed the integration of it over the interval. With that antiderivative, we did the derivative of it over, of course, this entire interval, and we ended up back at the original function. And now the remaining of these videos, I'm going to show you the derivative of integrals, but we're not going to do these loop procedures anymore. This right here is a loop procedure, which I call it, where once you have obtained your original function, we do the integration, then we do the derivative of the antiderivative to end up back. You don't have to do this. This is exactly what I'm talking about, the blind faith. In the fundamental theorem of calculus, you have to have that blind faith that once you've obtained your original function, if you were to hypothetically do this loop procedure, you'll end up back at the original function. But you don't have to test that out every time, because you should have the blind faith that the fundamental theorem of calculus, no matter what type of function is involved, will always be differentiable and will always be able to undergo integration process to end up back at the original function. Okay, here before us we have another expression over here for which we have to do the derivative of this integral. Now I'm taking these questions out from my single variable calculus textbook, and I'm going to show you how we do these type of questions. The question here in the book, and I'm reading it, it says exactly this. Use the part 1 of the fundamental theorem of calculus to find the derivative of the function. You have to find the derivative of this function. That's all what you have to do. And let's show you how we do these. You can do them in the procedure that I'm going to show you. And I'm going to show you over here very clearly, and I'm going to show you here in exactly the manner that I'm going to be doing it, in the manner that I've always done it. These type of functions are always in the form of t. The original functions will be in the form of x. Now you can use a chain rule over here. U is equal to x. Chain rule here seems a little unnecessary, but let's stick with consistency. It's unnecessary here because this variable in the interval is not composite by any means. Derivative u, d or du, we have substituted u over here, 1 over t cubed plus 1 dt, right? And then du over dx, you get a. And in all of these remaining questions, we're not doing the loop procedures at all. Now look over here, the derivative of x is just a 1. Here all you have to do is substitute u in place of t. Look, 1 over u cubed plus 1. Eliminate this 1 because it's kind of meaningless, and resubstitute what u's variable was, substituted variable. It's really x cubed plus 1. Therefore, the derivative of this integral leads you to your final function, or the original function, which is just 1 over x cubed plus 1. That right there is your final answer. So if someone were to present you this function, which is an integral expression, and they told you to find the derivative of it, this right here is your answer. Let's look at this question over here. There's a bit of a twist over here in that the variable is at the lower limit of the interval and the constant is at the upper end of the interval, and you want to have it the other way around. you want to rewrite this as this using one of the properties of integrals that I showed you, where you can use a minus and flip your interval around. 1 plus secant t dt. Now you can just do the actual procedure. You have to find the derivative of this. We have to find the derivative of this integral over here, because it will lead us to our original function. We have to determine what the original function is. You kind of have an idea what the original function is, because this is a non-composite function. You just put x over here, you'll get square root of 1 plus secant x, but you'll have a minus sign attached to it. But let's work it out and see it for ourselves. If u is equal to x, d over du, you have a minus, then u and 2. These constants are meaningless, because when you do the integration process, the constants lead to constant answers. When you do the derivative of those constants, they zero out. So don't get too confused by these constants over here. Unless there's a variable over here, then that's a different matter. You'll still have over here 1 plus secant t dt. Remember, I'm showing you the type of questions you'll see. These are always presented here in terms of t, but your final answer is always in terms of x. du or dx, you have an x over here. X is a derivative of 1. 1 hits with this minus, you get a minus 1. And this u will come right in place of this t, 1 plus secant u. You'll resubstitute back the x in place of u, and your final answer will be minus 1 plus secant x. So your original function was, for this question over here, minus 1 plus secant x. If you were to do the integral of this over this function, over this interval, and do the derivative of it, that loop procedure, you'll end up back over here. Now look here, in the rest of the questions for this video will make it slightly more challenging. We have a tan x here as the upper limit. If you want to do this, we're talking about here a question of determining the derivative of this integral. The question is, determine the derivative of this integral so that you can arrive at the original function. U is equal to tan x is our substitution, which makes us have a real legitimate need for doing the chain rule over here. But it's not hard by any means. D over du, and you have to substitute u in place of this tan x, because that's the substitution. Upper limit, lower limit, you still write t plus root t, because these things will get substituted, and then du over dx, tan x. Look over here. Tan x derivative is secant square x. You know that from the derivative videos. All you gotta do is substitute u over here. You'll get u plus root u. But then you gotta resubstitute back over here. What u is actually is tan x, right? So your final answer is secant square x multiplied by tan x plus square root of tan x. That right here represents your original function. Your original function was this: secant square x tan x plus square root of tan x. Now this is what I was talking about. If you want to now do the integration of this, arrive at an antiderivative and do the derivative of that to arrive back over here, you can, but the integration of this is not easy by any means. It's difficult, but you can be confident that you could actually do the integration of this over this interval and then do the derivative of the antiderivative and come back over here. So the fundamental theorem of calculus tells you that you are confident enough, or you should be confident enough, that once you arrive at your original function, it's good. You don't need to do that loop test anymore, because this right here is good. So here we have a function, right, an integral expression over this interval and this items in the parentheses, and we have to do the determination of the derivative. We have to do the derivative of this integral, because it will lead us to our original function, because that's what we're interested in. If you do the derivative of this integral, you end up at the original function. Look over here, the interval over here needs to be flipped, because I want that variable in the upper limit. I can rewrite everything as this. The whole question is really this: 1 minus 3x, 1 the lower limit, t cube or 1 plus t squared dt. This right here is really my question written in the proper way. We have a composite over here, or an expression. We can do u is equal to 1 minus 3x. Now we use the chain rule. Right here you have a u now, 1, and then t cube over 1 plus t squared. I'm not saying it's easy chain rule, I'm just saying it's not as complex as it became in some of those derivative questions where you have a chain upon a chain. You don't have that type of effect over here. Du with respect to x over here, 1 minus 3x. What's the derivative of 1 minus 3x? Is just a minus 3. You know that. You have a minus over here. All you have to do is substitute u in place of these t's. U cube over 1 plus u square. All you gotta do is now cleanly put everything. Minus 3 times minus is a positive 3. u is here 1 minus 3x. 1 minus 3x cube over 1 plus 1 minus 3x square. If done properly, other than the fact that you're ending up with some expression over here, other than that fact, everything over here should mirror exactly everything over here. You see how if you just remove the 3, everything here looks exactly the same as over here, with a bit of a substitution, but the general form is exactly the same. This chain rule brings a little coefficient which attaches at the beginning, but that's still part of your right answer. So this right here is your original function. Your original function is this. Now if you do the integral of this over this interval with the minus sign, and then do the derivative of the antiderivative, you'll end up back over here. But the integration of this is not going to be easy. It looks like not a very difficult function, but it is a difficult function, and the integration of that is just hard. So let's look at this question. We have to find the derivative of this function over here over the interval that you see. The question would be, basically you are finding the derivative of this expression. And look at the interval. We would need to flip it around. There's nothing wrong with flipping things around, because that's the better way of doing it. Upper limit should be the variable. Lower limit can be the constant over here. And then you have 1 plus t square cube dt, and this right here is basically your equation form. We can do a substitution. U is equal to cosine x. Remember, in all of these questions, they're proving that the derivative of an integral is equal to the original function. If you took the original function and integrated and differentiated, you end up back at the original function. If u is equal to cosine x, now we have everything marked over here. We bring a u1. We bring 1 plus t square cube dt, because all of this will be resubstituted here with the u values. Du over dx cosine x. Derivative of cosine x is a minus sine x. You have this minus over here, minus 1, same thing. Resubstitute the u over here, 1 plus u square cube. Substitute and solve over here. You get a sine x over here. What do you get in place of u? You get cosine x. 1 plus cosine square x cube. And this right here represents what your original function was. Sine x times 1 plus cosine square x, all cube, and you're done. This right here represents the derivative of your integral, which is the same. You're basically saying that this right here is equal to that right here, right? The derivative, actually let me make the notation good, because we were looking at the function here as g. The derivative in terms of the g is equal to your original function, right? If you were to do the integration of this over here and then do the derivative of the antiderivative, you'll end up back over here. But we don't need to do that, because we know the fundamental theorem of calculus tells us that this can go through that loop process and you can end up back exactly where you started. Now this question over here is tricky in the sense that look at the interval, they're both variables. You can look at this question right over here, and I'm going to use some abbreviations over here due to space limitations. You can look at this, and remember I talked about this in my properties of integral video. You can separate an interval like this. You see you have 2x, 0, f of u du. Don't worry about these letters, function with regards to u. I could have done f of t dt. Let's just do f of t and dt plus. We're splitting the interval over here. You see 2x to 0 and then 0 to 3x. I'm splitting that interval, and there's nothing wrong with you doing that. And look over here. I want to get the variable up. I can do the minus over here, and I can switch the interval around. So I can get, and these are interesting questions, you can get 2x over here and 0 over here. Now you have everything you need in terms of your equation form to actually do this question. And we're going to find the derivative of this entire expression, which means we're finding the derivative of all of this. Okay, you know you can do substitution. U is equal to 2x, and we can say v is equal to 3x. See, 3x and then 2x, and let's do it. The chain rule overhead. And we have a minus. Look, u comes over here. You have a 0. You have a t square plus 1 over t square minus 1 dt. And then let's finish this. With regards to x, we have a 2x. Now we have a plus, we're right over here. Now we have to do this with regards to v. D over dv, we have a v over here now, v, and a 0. We can write all of that again, t squared plus 1 over t squared minus 1 dt. Remember, once you're done with this, your final function will look kind of like in that form, except with the addition of these derivative aspects to it. And then you have a dv over dx. Over here you have a 3x. Now look over here. Derivative of 2x is a 2 multiplied by this minus is a minus 2. You can substitute u over here. We can do that. U square plus 1 over u square minus 1. This needs to be improved. Plus derivative of 3x is a 3. And you can substitute v's over here. V square plus 1 over v square minus 1. Now all we have to do is finish this up with the resubstitution of 2x and 3x in places of u's and v's. And let's do that. We have a minus 2 multiplied by u. Here was a 2x. 2x squared is a 4x squared plus 1 over 4x squared minus 1 plus 3 multiplied by v. Here is a 3x. 3x squared is a 9x squared plus 1 over 9x squared minus 1. What does this all mean? This right here is our original function. If you did the derivative of this integral over this interval, you'll end up as this as being your original function. If you were to take this through the loop process, do the integration, and then do the derivative, you'll end up back to this original function. But doing the integration of this function over here is not going to be easy by any means. And you can trust that the fundamental theorem of calculus is true, that this indeed is your proper function, and it would succeed through that loop process if you could do it. We're only going to look at this and another question, the last two questions, and then we'll be done. And these last two questions are a little more complicated. Just like the previous one in terms of the interval, we have to find the derivative of all of this right here. The derivative of this integral to end up at the original function. We want to know what the original function is. This right here kind of gives you a hint of what the original function would look like. Just the interval will affect the appearance of it. You want to start by manipulating this. And let's manipulate it such as how I'm going to show you. Sine x 0, always use 0. And you can follow what I'm doing over here. Sine x 0, 0 to 4x. Kind of like how I showed you in the properties of integral video, how I separate these things out. That's exactly what I'm talking about. dt. These functions here will be replaced by that. And you can flip everything over here using the minus sign. You can make your interval this. This becomes the lower limit to upper limit. 0 becomes a lower limit. F of t dt plus the limit over here, interval 4x upper limit is already set as we want it, with the variable in the upper limit and the 0 in the lower limit, the constant. Now all we have to do is substitution. U is equal to sine x, and let's do v is equal to 4x. Now look over here, d or du minus, this becomes a u0 cosine t squared dt, and then du over dx sine x plus, we're right over here. Now we look at this part, d or dv, this becomes 4x becomes a v over a 0 lower limit, cosine t squared dt, close this, and then dv with regards to dx 4x. Now let's finish this up. Derivative of sine x is a cosine x, with this minus is a minus cosine x. Derivatives again. Cosine t squared gets replaced with the u, cosine u squared. Right, you have this multiplying with the minus cosine x. Look over here, derivative of 4x is a 4. Cosine t squared actually becomes cosine v squared. Let's finish up with the final substitution over here, and then we're done with this question. You have a minus cosine x, cosine of u squared, which is a sine square x. See, cosine sine square x. We can put all of this in parentheses, plus 4 cosine v squared, which is a 4x squared, which is a 16x squared. And this right here represents your final function, which would be your original function. This carried through integration process over this interval, followed by the derivative of the antiderivative, will give you back this original function, but this original function should be right. One more question and that'll be it for this video. So we have this complicated looking function over here as our last question over this interval, which looks rather complicated. Secant x lower limit, x cubed upper limit. We have to find the derivative of this entire expression to understand what the original function is, and we can do the manipulation of this interval using the properties of logarithms to better situate ourselves to answering this question. Secant x up to upper limit of 0, f of t dt plus 0 up to x cubed f of t dt. And we can flip the interval over here using the minus effect. You know how to do that now. It's one of the properties of integrals. F of t dt plus 0x cubed f of t dt. If we're trying to basically understand what the original function is, we can do a substitution. If u is equal to secant x and v is equal to x cubed, we'll just use a chain rule over here, set everything up for completion. D over du minus, we have a u 0, 1 over square root of 2 plus t squared dt. With these t's over here will get substituted for the u. We have a secant x over here, and then plus right here plus. Let's do the v part, the v aspect of the chain rule. We have a v over here, 0, see v and 0, 1 over square root of 2 plus t squared dt, and then dv over dx, we have an x cube over here. Derivative of secant x, you know, and with the minus is a minus secant x tan x. This will get substituted over here with the u value, but let's skip that one step. U is equal to secant x, we'll get 1 over 2 plus secant square x. And then over here, derivative of x cubed is a 3x squared, and over here we'll get 1 over 2 plus t squared, which is what, x cubed squared, which is x to the 6th. If we want, we can write everything more cleanly by eliminating these 1 over parts, and we can do minus secant x tan x over square root of 2 plus secant square x plus 3x squared over 2 plus x to the 6th. You could have written this positive part first followed by the minus. That's just as fine. Perhaps it would be a better answer, and we can put right over here in the best format right over here. The original function would be this. I'm going to rewrite everything in a more acceptable format. 3x squared over square root of 2 plus x to the 6th minus secant x tan x over square root of 2 plus secant square x. This right here represents my original function. You can see, imagine doing the integration of all of this would be very tricky, let alone then the derivative of that. And that pretty much is our answer. 3x squared divided by the square root of 2 plus x to the 6th minus secant x tan x divided by the square root of 2 plus secant square x. So pretty much that's it for this video. In this video we were just focusing on the fact that if you do the derivative of an integral, you end up with the original function, and we focus on how you actually do the derivative of an integral by means of how you set it up. That's what I talked about, the setting up of these type of questions, because these are the type of questions that arise on exams and tests. So keep in mind everything I've talked about, and some of these questions based on the interval you have require the properties of how you can manipulate an interval by using the minus signs, how you can separate an interval into two parts by bringing in the zeros. So you've seen all of that in this video. And then I also talked about, in terms of the very first two questions, using your original function which you've derived, you can do the loop process, integral and derivative, to come back at the original function. So all of this has been presented to you. In the future videos we'll actually get into the techniques of integration with regards to the different function types that are present, and those are the videos to look out for. I hope you enjoyed this video. Have a nice day. Thank you for watching. Bye.